In this video, we're going to explain the numerical solution of linear regression, which can be found via gradient descent. If you would like to listen more about the representation of linear regression and how it can be solved via in analytical form via a closed form solution, please feel free to watch the previous video. So in this video, first, we're going to provide some general details about the gradient descent algorithm, and then explain how this algorithm can be used in order to solve the linear regression problem. Finally, we're going to provide three types of gradient descent for linear regression, namely the batch, the stochastic, and the mini-batch gradient descent approaches. So why would we like to use an approximate solution to solve a linear regression problem rather than the closed form solution? The first reason could be that the closed form solution is computationally very expensive to calculate. And the reason is that, as we have seen, this is the formula of the closed form solution. And this formula contains the inverse of this D by D dimensional matrix, which is D refers to the number of attributes in our feature space. If D is very high, then also this inverse will be computationally very expensive. Another reason is that this X is the data matrix. So this X has as many rows as the number of samples and as many columns as the number of dimensions, number of attributes in our data. When we compute this X, this formula X transpose X, it means that we need to do a multiplication of a D by N dimensional matrix and an N by D dimensional matrix. Therefore, computationally again, the cost would be very high. And another reason why we demonstrate gradient descent in linear regression is that usually optimization problems in machine learning do not have closed form solutions, such as the ones in linear regression, and therefore demonstrating gradient descent in this single problem will actually be beneficial for later problems as well. So overall, when using gradient descent, we can solve a problem, an optimization problem that is being characterized by a function j of w. W is the vector based on which, with respect to which we would like to solve our optimization problem. And this vector w can belong in a d-dimensional space, while this function j of w at the end will have a scalar form. So we would like to find the minimum of this function j with respect to w. And the goal of linear regression is to do so via a greedy local search. Gradient descent is a method that is very widely used in optimization problems and in many machine learning applications because it scales well to large data sets, since we really do not require this vast matrix multiplication that we have used, for example, in linear regression as part of the closed form solution of the problem. There are some proofs that it solves many convex problems, which is something that is always beneficial for optimization algorithms, and it also has a good heuristic to non-convex problems. So in this one-dimensional example, we have this quadratic equation here. Our input space is just a one-dimensional variable w, and the cost function is this j of w, which is represented by this polynomial function here. So we would like to find what is the position of w that minimizes this polynomial function. This is one of the simplest minimization problems from our calculus. We could solve this optimization problem by simply finding the first order derivative of j with respect to w, but we are going to see how we can do this in an approximate manner through gradient descent. So let's say that we start from a random place of this optimization function. Let's say that we start from this place that I'm showing with my cursor here. What we want to do is essentially we want to either move to the left side of the cursor or to the right side of the cursor. And by doing so, we want to see whether if we move to the left side, if G of W increases or decreases, and vice versa, what happens to G of W if we move to the right side. So essentially, we want to slightly move our the position of our next vector W such that J of W decreases. And gradually, we would like to keep shifting our vector W, our solution W, such that we find this, this minimum of the function. So, this is another example in which we have a little bit of the more complex functions, and we have again a one-dimensional example. Our input is again the vector W, but J of W, we can see here that it has two local optima, one global and one local. So let's say that we start with this from this place W0, and we would like to find where to go next, whether to go on the right side of W0 or on the left side of W0 in order to get the minimum of function J of W. So the way to do this is actually look at the first order derivative or the gradient of J of W when computed at W0. And in this specific one-dimensional case, the gradient of J of W is essentially the tangent of our function J of W at the place W0. So what we can see here that is we have this tangent, and this tangent actually has a positive slope, which means that if we go to the right side of W0, then the function J of W increases. Inversely, if we go to the left side of W0, then this function J of W will decrease. And essentially what we would like to do is, informed by the positive slope at W0, go to the left side, because we expect that the J of W will decrease at least locally when we shift W0 towards the left. Similarly now, if we start from W1, we see that the gradient of W1 is negative. So this means that if we slightly shift W1 to the left, we will have an increase of J of W, and if we slightly shift W1 to the right, we will have a decrease of J of W. And because of that, we can decide to shift locally W1 towards the right side, towards this right side. So essentially we see that the sign of the gradient can be what determines whether to shift our search space towards the right side of W or the left side of an initial point. The above procedure can be repeated until we reach at least a local minima or a global minima from our starting point. So here we also show how this happens. For example, if we have the gradient of our function J with respect to W, this gradient is actually defined from this fraction here. So for a small positive epsilon, it's the difference between J of W plus epsilon minus J of W divided by epsilon. And that's from calculus, that's the definition of the first order derivative. Now, if the first order derivative of J of W is positive, this would mean from the definition that J of W plus E is greater than J of W. Therefore, this means that if we slightly shift W and make it W plus E, since epsilon is greater than 0, then essentially this function will increase when we slightly shift W towards the right side. However, if the gradient is negative, this will mean that this function J of W will actually decrease when we shift W slightly on the right side. Therefore, the derivative of G of W can be used to decide which direction to move when we look for a minimum for the minimum of a cost function in our gradient descent. So every time we have to move towards the positive direction of the gradient. Now, this can be formalized in this one-dimensional case that we just saw as follows. Let's say that we have, again, an optimization problem, a function, a cost j of w, and we would like to minimize it with respect to w. We can initialize this w randomly, and then while the first order derivative of j with respect to w is greater than 0 or greater than a very small number epsilon, we can keep looking for w at the opposite side of the derivative. So when we have, so essentially this is represented by the opposite side of the derivative is being represented by this vector, this notation minus dg of w divided by d of w. So another thing here is that this fraction, dj of w by d of w, might have an arbitrarily large or an arbitrarily low value, which might not be actually proportional to w. So what we can do is multiply this by a learning rate alpha. So if this learning rate is very high, this means that this fraction will be very much significantly affect the shift over w. Otherwise, this fraction will not significantly affect this shift in w if alpha is close to 0. So here we can see essentially that every time at every step, we move w towards the opposite direction of the gradient. And by doing so, eventually we can find a local minimum to our problem. Now, if we are to expand this in the d-dimensional case, instead of having the one-dimensional w, we can have a vector w on a d-dimensional space. Instead of having a first-order derivative, we can have the gradient of g of w. And again, this gradient vector, again, is a d-dimensional vector. And now, instead of shifting w only towards the left or towards the right side, we shift w across the d-dimensional space via, again, a direction that it is opposite to the direction of the gradient vector. Just as a gentle reminder, this gradient vector is of dimension is again a d-dimensional vector. Therefore, this math here holds because w is also a d-dimensional vector. And here we can see an example of a function that we can of a two-dimensional function that we can solve and find its minimum based on the multi-dimensional gradient descent. In this example, we also demonstrate what happens when we change the learning rate for our gradient descent too fast or too low. So in this case, we can, when alpha here, for example, is 0.1, and we have this quadratic loss here, we start from this point that is being depicted by the cursor. When alpha is 0.1, for this example, this alpha is pretty low. Therefore, the change in W, we search in our search space in a very slow pace. Now, when we increase our alpha, then we don't need as many iterations to go over our solution space and find the local optimum, which in this case is also a global optimum. The more we increase the alpha, the less number of steps we are likely to do, but there is a catch. So we cannot arbitrarily increase alpha, because if we do so, then actually we might have oscillations like that. In this case, because we increased alpha, the learning rate too much, we went from one side of this quadratic polynomial right next to the other side. So essentially, from there again, it was a little bit harder to converge. So how to choose alpha, which is the learning rate? A very easy way to do so is to use a development set and see what alpha works best in our development set and use that and apply that to our test set as well. Or another way to do that is through a cross-validation framework, especially if we have an overall small number of samples. Another point here is the stopping rule. So we said that we are going to stop we're going to stop when the magnitude of the gradient becomes less than a very small number epsilon. But actually, what is small? So in practice, we can choose epsilon. Again, we can assume that epsilon is a hyperparameter, and we can find epsilon based on a development set or based on a cross-validation. We have to note here that if epsilon is very small, then it might take us more iterations in order to reach our solution, just because this gradient vector has to become very, very small. On the other side, if epsilon is very large, then it will take us less iterations, but we might not find the most reliable solution. Here we also provide a distinction between the parameters and the hyperparameters of the model. We understand that the model parameters are the parameters that are being learned during the learning process, and this referred to the weights, for example, of our model in the linear regression algorithm. However, the hyperparameters are set before the beginning of our experiment, before the beginning of our learning process, and are being learned usually via a development set or via cross-validation. In the case that we have discussed right now, the hyperparameters can be the learning rate alpha and the stopping rule epsilon of the gradient descent. So hyperparameter tuning refers to the process of choosing a set of optimal hyperparameters that will be eventually used in the learning process, which is the process of learning the weights W from the training data in the linear regression. So let's see now how this can be applied in order to solve our linear regression problem via gradient descent. Again, based on what we discussed, what we need to do for every gradient descent method is essentially find this gradient vector of our optimization function. And once we find this gradient vector, then we keep updating our weight, we keep updating our unknown variables using this gradient vector, and of course, with our learning rate and our stopping criteria. So essentially what we need to do is find the first order derivative, which we have already found from the previous part of our lecture, and substitute the first order derivative in that first equation here. So this is actually all we need to do. Then we keep running this update rule as much as we can in order to find the minimum of our problem. Now, instead of computing this first order derivative for all our data, which can be computationally, again, very expensive, especially if we have a large number of samples and a large number of dimensions, we can actually use a subset of samples in order to compute our first order derivative. So this is usually referred as mini-batch gradient descent, which we are going to see right in the next slides. So what we have seen so far is what we call batch gradient descent, which means that we keep updating our weight based on all our training data until our model converges. So moving forward, we're going to see what happens when we update our weight based on only one sample at a time instead of all our data. So according to this method that is being called stochastic gradient descent, we initialize our weight W and we keep updating our weight now instead of using all our data samples based on a randomly selected data sample. This process is repeated until our algorithm converges. Now, the main problem with this is that it might take us a while for the algorithm to converge, just because the update rule is only based on a randomly selected sample, and this sample might be an outlier or might be not always a sample that's being representative of our data. So in order to mitigate this, we can use what we call a mini-batch gradient descent. And the main rationale behind the mini-batch gradient descent is to use a randomly chosen subset of samples for the same update rule. So here, if this set S corresponds to a randomly chosen set of samples and a randomly selected set of samples, then we can form this mini-batch data matrix X of XS that only contains the data samples that belong to our set S. So then when we update the weights, we have exactly the same update rule that we had in the batch gradient descent, but instead of having here our data matrix X, we have our mini-batch data matrix XS. Something to also mention here is that, as we have most probably figured out so far, gradient descent does not always guarantee that we can find a global optimum. Gradient descent is a locally greedy algorithm, therefore the initialization point and the learning rate and the stopping criterion can all affect the quality of our solution, and can also affect whether our solution is going to be a global minimum or a local minimum. So thank you so much for looking at this video. As part of the next video, we are going to discuss about the nonlinear regression and about overfitting and regularization.